phase estimation. The floor is yours.
Hello. Is it loud? Yeah, I open it. Okay, cool. All right. So thanks for the introduction, and thanks for organizing this amazing event. I'm Yukuan from University of Nottingham, and today I want to present to you about this recent work that I've been doing with my PhD supervisor, Marlene Guta and Gerardo Alesso. It is already out in the archive, and so if you're interested, you can check it out, the detailed work. I'm going to split this talk roughly into two parts. The first, I want to talk about how this complexity and energy trade-off relation arises in general and how you can apply it to relevant quantum protocols. And then I'm going to talk about how to actually apply it to a quantum protocol. And we take the quantum phase estimation from metrology as an explicit example. Okay, so first, what do we mean by complexity and energy trade-off? We'll be sticking with the standard circuit model for quantum information processing task. And the picture in the middle is just a typical example of a quantum circuit consisting of unitary gates that's selected from an elementary set. And we define our complexity as the minimal number of such elementary gates that you need to reach a desired target. And we denote this complexity by the symbol C. Of course, it's really relevant in many common fields of studies, such as quantum computing, metrology, and quantum simulations. And then naturally, each gate will take some energy for us to implement. As we've seen in the talk so far this week, this energy comes in many different forms. It can be the thermodynamic cost. It could be the energy of the control to manipulate the systems, and so on and so forth. And we just, in general, denote this energy by the symbol E. And accordingly, we can define this total energy cost R as the number of gates times the energy of each gate. Of course, we make a drastic simplification here, where we assume each gate takes the same amount of energy to implement. Of course, more realistically, there can be much greater flexibility in this energy distribution. For now, we just stick with this simplification, which turns out can already provide enough illustration on how this total energy cost behave for our concern. So far everything is in the ideal scenario where we assume we can implement these gates exactly. However, in reality, there always exists this implementation error that arises from all kinds of sources of noise. For example, there's decoherence from system-environment interaction, and our device can also be imperfect from a finite resource constraint. And so as a result, the actual quantum channel we're going to implement is going to be non-unitary, and we quantify this deviation from the implement channel from the ideal unitary form by this error parameter epsilon. Epsilon is very case dependent. It might depend on multiple factors. Here we just really use a symbol to quantify this error. However, empirically, there does exist this general trade-off relation as we increases the error parameter. That's been studied in many different works, and they mostly follow the same pattern. And that is, as it increases error, the complexity of a quantum protocol will increases. So in some sense, there will be more information leakage from your system to its surrounding. And so we need to implement more gates in order to gain a set amount of total information. Meanwhile, the energy cost for implementing each gate will decrease because intuitively you're spending less energy on suppressing this error. So as you can see, there's this competition between the two factors, and there's a trade-off between them. When you combine them together, the total energy cost will also has this error dependence in the end. And we'll be interested in scenarios where, as we increase the error, this total energy cost will go through a drop first, but then eventually it will either plateau or grows in the end. And this is interesting from an energy perspective, because if we want to minimize the total energy cost of a protocol, it turns out that a finite level of implementation error is actually preferred, instead of trying to eliminating the error completely. So now we have a qualitative idea of how this sort of trade-off relation works. We're going to briefly summarize all the essential ingredients we need to apply this framework of trade-off. So first, we need a metric that depends on this error parameter and the number of gates in our quantum circuit. Of course, this n here can also have some sort of property of spatial arrangement. We just summarize everything in this symbol again. And we use this metric to quantify our desired goal that we want to reach at the end of quantum protocol. And according to that, we can define our complexity as the minimum number of gates we need for this metric to reach a desired threshold, M0. So the expression is given on the screen here. And then as for the energy cost, we just need an explicit physical scheme of how to implement these gates and from which we can read off the energy cost of each gate right away. So as you can see, there's really only a few ingredients that we need to apply this trade-off framework to quantum protocols. So it has a really wide range of application as long as the protocol at hand has a clear notion of gate complexity. Okay, so now we know how exactly to apply these ideas. We're gonna jump into a specific example to see how it works in action. And for this, we choose the sequential quantum phase estimation protocol from quantum metrology. And we'll be sticking with a very simple toy model, which is still enough to illustrate how this trade-off relation pops up in the end. So what's happening is we have this unknown parameter g that is encoded in a unitary operator as a phase vector. So it'll be e to the minus ig power x over 2. And then every time we make a query, this unitary operator is repeatedly applied to a probe qubit that we initialize in the 0 state. So by the end, the final probe state will contain accumulating information about this unknown phase g, and we try to extract it from post-processing of our measurement outcome on the probe. And to assess our estimation performance, we choose the metric to be this very popular candidate, the quantum Fisher information, or QEI. So roughly speaking, it captures how sensitive of our qubit, and if we just change our unknown parameter g by a little bit. And for our purpose, what makes the QEI useful is the well-celebrated quantum Quinn-Morrell bound. It states that the variance of the estimator of an estimator on G is lower bounded by this quantity on the right-hand side of the inequality. So Fn is the QEI at the end of a sequence that consists of n steps, and Q is the number of times that we repeat the sequence independently. And so in this case, the total number of gates is just the number of sequence times the number of gates each per sequence, Q times n. So now we have this metric. We should be able to compute the complexity. And next, we just need to come up with an explicit physical scheme of how to implement this QPE protocol. And for this, we first need to give a physical meaning to the unknown parameter g. And for this, we take g to be the coupling strings between an electromagnetic field and a qubit, which interact through the standard James-Cummings model in the resonant case. So as we know, if your field is classical enough, or its amplitude is large enough, we can make the so-called semi-classical approximation where we replace the field operator with the classical expectation value. So E0 is the amplitude of the field and phi is the phase. And in the semi-classical regime, we can implement the desired unitary gate exactly by carefully tailoring the field parameters and the evolution time. However, an approximation is an approximation after all. So there's always this implementation error that arises from the quantum nature of the field, and which deems a perfect unitary implementation to be not possible because of the field fluctuation. And to model this implementation error, we first take the field to be in its coherent state, which means the sequence will represent a sequence of laser pulses, each pulse with a mean photon number m bar. And the semi-classical regime we just talked about corresponds to this m bar goes to infinity, which is of course not possible in reality due to a finite energy constraint. And in this sense, we can sort of try to represent this implementation error by the inverse of our m bar. This will not be a rigorous definition in terms of some distance measure. It's really just saying these two numbers, these two quantities, they follow the same trend. So we can use one to represent the other. And finally, with these, we try to compute the actual channel that we implement with a compromise between classical and the quantum by treating the amplitude and the phase of the field as random variables that following a very sharply peaked normal distributions that is given by the coherent state. And so the channel can be computed as a probabilistic mixture of unitary channels. And now we have these ideas, we can summarize. And so it turns out that the channel, the action of the channel on the Bloch sphere is quite simple. It can be well approximated by a desired rotation around the x-axis. So it's the unitary channel that we want to implement, followed by an anisotropic shrinking in the three directions. It will be isotropic in the YZ plane by a factor r perpendicular, and a different shrinking factor in the x-axis are parallel. And it turns out the QEI in this case now depends on the error parameter, the inverse of the photon number, by this expression given in the middle. So we see initially it'll go through a quadratic growth, which is the standard Heisenberg scaling. But then you'll eventually go through exponential decay due to the shrinking factor are perpendicular. And these expressions are roughly approximated by the expression given on the screen. So now we know how to compute our metric, and which leads us to be able to compute the complexity. We finally just need to define what do we mean by the energy cost of implementing each channel. This is the final missing ingredients that we need. So for this, we resort to the interpretation of the energy cost from a conservation perspective. Pictorially speaking, what's happening for each gate is that we couple the probe at this time with the field. They go through these James-Commons interactions together, and by the end, we toss the field away, and the probe, the output probe is taken as the input probe for the next gate. So in this perspective, the JC interaction itself is a free evolution. You just let the field and probe do whatever they want. So all the energy cost from this conservation perspective is the energy we need to prepare this field. So if you assume the field starts in its vacuum state and then apply a displacement operator for it to reach the desired coherent state, then this energy change of the field is really just the number of photons times the energy of each photon, so h omega n bar. And we'll take this as our energy cost of each channel. Of course, there's many different other ways to also incorporate other sources of a cost. For example, there's also energy of maintaining the field, such as the drive force. But for now, we just keep this very simple notion of energy cost in our work. So now we have both the complexity at hand and the energy cost of each channel. And when you combine these two together, leads to the total energy cost of our quantum phase estimation protocol in a sequential setting. So the horizontal bar on the plot is the error parameter, or the inverse of the photon number. And then in the inset, you can see that as expected, when this error increases, the complexity keeps increasing in the end. However, in the big plot, for the total energy cost, it diverges in the ideal limit, which is the semi-classical regime that we just described. It goes through a drop first, but then eventually it plateaus after a certain point. So what it's saying that if you keep reducing the photon number that you spend on each gate, eventually you're not going to save any more total energy cost. And so it just saturates after this sweet spot that we defined. And why we say it's sweet spot for a complexity energy co-optimization is that beyond this sweet spot, you cannot save any more energy, but in the meantime, the complexity still keeps growing up to this point. So by sticking with this point, you can sort of keep both quantities as small as possible. And the total energy cost of this plateau can be roughly approximated by the quantity there, denoted by R0. And then this gives a very natural connection with the MNR framework that was raised by Marco a few years ago. And the key component is this energy efficiency eta, which is defined as the ratio between the metric and the resource. We have them both explicitly defined in our case. And so after you do this ratio thing, it turns out that the efficiency in our case in this particular protocol is independent of the metric value and only depends on this unknown parameter G. And we can use this number to quantify how energy efficient this particular optical platform is to perform our estimation task. So finally, I just want to briefly mention that the gate there's many other external costs apart from the gate implementation. And so we use a very simple model to quantify these other costs, such as the preparation cost for the probe and the measurement cost on the final state of the probe. I'll try to skip this part first because it's really primitive study. So this is what we've done so far. There's many natural extensions from after this point. For example, for now, we're just tossing the field each time after we implement the gate. This is probably a very big waste of energy. So it would be nice to come up with some sort of recycling techniques to restore the field back to its original state as close as possible and use it for the next implementation. And we also don't have a control on the qubit, which can also, this error mitigation control can also be used to help improve the estimation by suppressing the error. And we also want to include more practical settings where other sources of noise are taken into account other than the quantum fluctuation of the field itself. And then so far, we've only taken energy as our resource quantifiers. There's also many different types of resources in quantum field, such as entanglement, coherence, and magic. So we want to come up with a more general framework where we can define this resource complexity trade-off instead of just energy complexity trade-off. And finally, as we claimed in the beginning, our protocol, our trade-off framework can be applied to a wide range of protocols where there's a clear notion of complexity. So I think it will be interesting to see if it can be applied to other common quantum tasks. Before I finish, I just want to quickly mention there's this student-organized conference that we're doing at Nottingham right now. It's aimed at early career researchers, so postdoc, PhD, master, maybe undergrad if you are crazy good. We're going to talk about everything about quantum, and if you want to share your work with your peers and know what they're doing, feel free to register. I know it takes place at the same time as the Italian Quantum Information Conference, but if you want to betray your countries, you're more than welcomed. And finally, I was told there's this page is to show that the social dinner is going to be on a boat, which apparently is the highlight of the conference. So if you want to come for the boat, it's also good enough. That's all. Thank you.
Thank you for the very nice talk. Maybe we have time for a couple questions max.
So to saturate the Kramer-Rao bound, you need to do optimal measurements,
Yes.
which are sometimes difficult. So how do you ensure that you have in fact saturated the bound?
Yes, that's a good question. It's very important. So for more accurate statistical assessment, as you said, we need to look into, for example, the convergence of Kramer-Rao bound and how to determine the optimal measurement through adaptive fashion. But in this work, we're really just using the QEI as sort of a metric or a number to give us a goal to reach to determine our complexity. So I would say, yes, indeed, the actual variance in our case is not too greatly reflected by the Kramer-Rao bound. And for a more detailed study, we think we need to generalize this metric to a more sophisticated fashion. But for now, we're just, in this work at least, we just use it as a number, really. So sorry for the disrespect to the quantum Kramer-Rao. Thank you.
Hi. Do I understand correctly that because the only source of the connection between energy and errors that you took into account was a very fundamental one of there being just not enough photons in the field? Yep. So that's, I guess real lasers have many, many errors that are not of that type.
Yes.
So this is a really fundamental, underlying physical thing. So
exactly.
Did you estimate the resources in watts? Because a typical laser is maybe milliwatts. I guess this is like picowatts or really, really small, right?
I understand. Yeah, no.
But did you get the numbers or did you?
Yeah, unfortunately not. But yes, I think to make an actual experimental connection is also a big, I didn't mention, but it will be a big interest of ours as well. For now, I can say is that we're looking into photon numbers of about at least 100 per gate. Mm-hmm. And the ratio between this unknown parameter and photon number will be small, so it'll be G equals around the order of magnitude of 1. But yeah, in terms of actual volts or the frequencies, we haven't looked into much, but yeah, it'll be nice too.
Yeah, so this is something like a sort of Landauer limit for classical computing, which is almost unachievable, but it tells you what real laws of physics give you as a limit. Okay, very nice, thank you. Yeah.
Thank you.
So we thank the speaker again.